Right. Hello, everyone. So I gave an invited keynote presentation. I was fortunate to give a keynote at the ASNT conference this year, 2023. So this was the ASNT Research Symposium conference. And the presentation I gave, it was a bit of a longer one. So it was, I think, scheduled for 45 minutes. But a bit of a longer presentation, so that gave me more of an opportunity to get a bit of depth. And I tried to make it fairly kind of tutorial focused, so get across some of the background, some of the kind of underlying concepts upon which some of the research in imaging and tomography is based. So because I've got all that in there, it felt a bit of a shame to just give the presentation once. I thought it might be useful for people in the future to have some kind of record of it. So hence I am recording it here. So as I say, it's been a few months since I actually looked at this, so maybe I won't be able to remember everything in as much detail, so do bear with me, but nonetheless I will do my best. But yeah, the topic essentially is, as you can see here, so ultrasound tomography for NDE. Tomography itself, the concept of tomography has been looked at a lot within radiographic CT. So if you say tomography to somebody, usually I'll be thinking about radiography or other methods. Radiography makes things a lot easier because it's nice straight lines. Generally, well, we neglect things like scattering and so on when we do the reconstructions, but that makes it a lot easier to, I suppose, conceptually understand and process. Whereas with ultrasound, you can use some of the same concepts in certain places. You can do some approximations, but you do get other effects such as refraction, diffraction, and all sorts of things. So that's really where the ultrasound tomography part comes in. And in terms of applications of ultrasound tomography, you can do a lot across several different areas. So geophysics, they do a bit of, I think, what they call ultrasound tomography, or seismic tomography, I suppose it would be at those sorts of scales, but I mean the equations scale. And in medicine as well, there's sort of a growing area of ultrasound tomography for medical applications. If you're interested, ask me. I know a good PhD thesis on that. But specifically, the NDE, non-destructive evaluation aspect, is what we'll be looking at in this talk, and how ultrasound tomography can be used for those applications, the sort of specifics. So without further ado, why do we want to actually do ultrasound tomography in NDE? This is one of the kind of main applications, certainly that I've researched through the years. This is corrosion mapping, and the concept you can see here is you've got a big pipe. Doesn't need to be big, it could be smaller, but essentially you've got a pipe resting on the support like this, and you get water collecting around underneath that support, and that causes corrosion in this particular region here. Obviously that corrosion is problematic. You want to be able to measure it. If it eats away the wall too much, that's going to be problematic for industry. So basically the oil industry is very interested in knowing what the minimum remaining wall thickness is, to be able to say, is it safe to continue using the pipe, or do you need to stop it, turn off your plant immediately? Are you safe to get through till next shutdown, for example? And there are big cost implications associated with these things, obviously with safety as well. So yeah, essentially this is the challenge. And traditionally what you'd do is you'd empty out the pipe, lift it up, and go along and take point measurements at lots of locations using ultrasound, basically reflecting off the back wall, assuming you know the wave speed and getting the thickness in that way. In what we're proposing to do instead is to send guided waves underneath this support, and utilize the information coming from those guided waves being scattered to try and reconstruct a map of thickness in that region, understand what's going on in that region. So the guided wave tomography kind of setup, what we usually think about is having a 2-ring arrays, transmitter and receiver, either side of the support location, with a potential defect there that you can see in the middle. What we usually do is neglect the curvature of the pipe, which is a valid assumption for most of the cases we're looking at, and essentially flatten the pipe out, unroll it into a nice flat plate that you can see here with one transmitter and one receiver array either side of the defect. We've done some work on that sort of setup. In this talk, we'll actually be simplified a little bit to look more at the kind of underlying theory, and we will look instead at having a nice circular full view array around the defect that you can see here. We then want to somehow produce this map of thickness that is of interest to industry. What we usually use is the fact that the guided waves are dispersive. So this also requires a bit of knowledge of guided waves. These are some dispersion curves, and essentially what you have here is that the phase velocity, which is one of the velocities of the wave, is a function of the product of frequency and thickness. So just to highlight, we've drawn a couple of the fundamental modes here. You've got the A0 mode, which is a fundamental bending mode that you can see, and you've got the S0 mode, which is more kind of longitudinal mode. That's kind of illustrated up here. So we've got these two modes, and the point is that essentially as you change frequency, you get a variation in the velocity. Similarly, if you change the thickness, then you get a variation in the velocity. Obviously, the product together effectively normalizes this, makes it dimensionless, and you can get this sort of plot like that. For guided wave tomography, what we do is we pick a particular frequency. So in this case, we're just happy to pick 50 kilohertz, which is one commonly chosen option, and we can, through some method that I'll get on to discussing in due course, we can reconstruct a map of velocity from our measurements. So send all these waves in different directions, produce a map of velocity somehow, and then we can convert that velocity map into thickness by using this dispersion curve, this relationship, as a sort of lookup table, if you like. You can kind of interpolate, go along from phase velocity, look up what the corresponding thickness is. And that's quite a common approach that's been used for many years in guided wave tomography. Another area of application for tomography methods is early stage damage quantification. So the idea here is that you've got some block of material, and somewhere in there you've got some early stage damage, and this is pre-crack, so we don't have any kind of sharp features or anything like that in there. We want to try and detect this and quantify it. And what we can do is we can put an array above. I suppose you can have a single crystal element if you want, just one transducer, but we're going to go for a full array and try and do some more imaging type work. And what we can do is we can send in waves from that array through this potentially damaged region and try and quantify it. What we'd normally look for are these sort of sharp reflections from a crack or a void or some other traditional NDT defect. But we're going to say, because this is early stage damage, we don't have a sharp defect, so we really don't get very much reflected from it, and it's often a very gradual boundary as well, so you don't see very much in the way of reflections. But what we can use instead are the waves transmitted through this region, reflected off the back wall, and measured back at the array like this. So that's our kind of setup, and that gives us access to this kind of transmitted data, which should encode some information about what's going on within the defect region. To simplify this down, we actually unwrap this in effectively do this kind of mirroring approach, where we have a source array above and a receiver array underneath that you can see there. And the key thing to note about this is that we've now got a slightly different configuration. Whereas before we had, or we set it up to have a full circular array all the way around, so you can get information from all the different angles. In this case, we've only got information coming from above and below. We don't have anything going from the two sides. So this means we've got some kind of limited data problem. We're missing information, and that's a potential challenge. And this is something that we'll look to overcome later on. So the talk, essentially, having given a bit of an introduction to some of the applications, we'll go into three different areas. We'll first of all look at background concepts and tools that will then essentially be the basis to help understand the standard tomography algorithms. And then we'll also look at how these are then extended into new tomography approaches, some of the kind of more recent research that's been done in this area. So first of all, the background concepts. We're going to look at the total focusing method, or beamforming, which is fairly, or essentially is certainly the most common ultrasonic imaging method, I would say. Essentially, pretty much all algorithms have some variation on this in some way. It's also known as delay and sum. It's as I say, beamforming. Pretty much, it's very common across other fields. I think Kirchhoff migration as well in geophysics might be the same as well. So it's known by a lot of different names. So we'll cover that. We'll also talk then about the plane wave approximation and actually applying this to the total focusing method, because that comes in useful later on. Briefly mention time and frequency domain stuff, and as well the Born approximation, what that actually means for our applications. So basic image generation. So this is the total focusing method. What we have here is a grid, and in this grid we want to try and produce our image. So this is actually a grid of pixels, obviously quite big pixels here just to kind of illustrate it. And we've got our array above it. And the concept is we pick a pixel first of all, so I've highlighted one down here, and we want to try and generate an image value for it. So what we actually do is we can time delay the transmission up here on the array to focus at this particular point. So to do that, we need to know the distances from the point to the array. So you can see that we've got two different distances here. We've got the kind of closest point to the array and then the furthest point away. And we can then delay sending signals from each of these separate elements in our array such that they will arrive at this point at the same time. So you can see this kind of illustrated. This is obviously just an example, but you can see it's illustrated here. And hopefully these waves should then all arrive at that one point at the same time and have a nice strong focus. Then if you have a scatterer there, you'll get a scattered signal from it, and this will then scatter out and be received by the array, and you can time delay the received signals as well. So obviously if it's scattering from that point, you're going to get the same sort of time delay across the receivers, and essentially that time delay will then align all of your signals, assuming they've come from the scatterer or that pixel. And then you just sum them all up, and if they're nicely aligned, you should get a very large, strong response from that sum. And if there isn't a scatterer present, but maybe there's a scatterer somewhere else, then they won't be coherently aligned. They'll be kind of distorted in different directions and things, so you won't get a strong summation. You won't get the same focusing effect. So that's basically the concept. And you see the idea of delay and sum now, so that's where the other names sort of start to come in. This is represented mathematically down here. I tend to avoid doing too much maths in these slides, but sometimes it's a little bit necessary. I'll run through what we've got here. Essentially, you've got our imaging point is point X that you can see here. You've got our source points. This would be for one particular element, XS for the source, XR for the receiver. And essentially, so you can get these two distances, then sum them up. So sum the source distance, sum the receiver distance, divide those both by c, which is our wave speed, and pick out the value from our signal, our received signal at that particular point in time. So essentially this process aligns all of our signals. So that's what this distortion is doing. And then this is the summation process. And then effectively this gives us an image, total focus image method at position X that you can see here. The next part I want to mention is the plane wave approximation. So here we've got our full view array. So whereas previously we did have in fact, previously we had a nice linear array to keep things simple. Here we've got a circular array. And the point to note here is that if we've got a fairly small scatterer, which sometimes is the case, then you can actually neglect the curvature and treat these as plane waves. This doesn't mean that we always have to have this assumption, but for the theory that I'm explaining here in this presentation, it's a much easier thing to think about. But as I say, we can bypass that later on. But in terms of understanding the theory, this is what we have. So as I say, we're neglecting the curvature here, treating it as plane waves. And then how do we image with that? What consequence does this have for the total focusing method? Well, out here we've now got a source which we've got into the far field, so a long way away, such that when the waves arrive at the center, they're effectively planar. So this is where our scatter would be. And similarly, and one point to notice that we now define our source direction really, rather than a sort of source point. We just have a direction describing what direction this is coming in at. And if we then have our imaging pixel, which is position x, so given by this vector shown here, we can then calculate our source distance utilizing this little dot product now. So we've got the main part, which is our radius r from the source to the center. So that's actually going to be constant for all the points in our array, assume it's a nice circular array centered on the origin. But then you've got this vector x for the position of the pixel. You've got ss being the direction of the source, and you can just do a dot product of the two, add that onto r to approximate our total distance. And this works because of the plane wave. Okay, and on the receive side, you've then got essentially pretty much equivalent. By the time the waves scatter out from this central point, we treat them as planar at the receiver array. And we've got our receiver distance as being r, and now it's minus sr, which is this vector here, for our receiver direction. Okay, and we can put these together. So essentially summing up these two distances, we now get 2r plus this dot product. So ss minus sr dotted with x, and this is again quite useful for what we'll see going forwards. I will briefly mention the time domain and frequency domain, but I won't go into too many details about the consequences. So far, everything I've shown has been effectively in the time domain, where we time shift signals or pick particular values at particular times. Effectively, that corresponds to a convolution with this delta function. So shifting means you can convolve with a delta function in order to shift a signal. In the frequency domain, the kind of equivalent, if you Fourier transform that, is multiplying by this exponential term. So this is I, imaginary number, omega being our angular frequency, multiplied by these. So effectively, you're doing a phase shift on your signal, which is the same as doing a time shift in the time domain. So we can basically convert our total focusing method algorithm into the frequency domain. And so this was the time domain version of it, and in the frequency domain it essentially becomes what you can see here. So essentially you can see this is all effectively exactly the same, but now rather than a time shift we express it as a phase shift and multiply it by our signal. Just to mention Kac-and-Slaney here, don't know if you'll be able to see that. So mention the Kac-and-Slaney textbook. Principles of computerized tomographic reconstruction is available online. It's a very, very good reference, and I would recommend that you have a look at it because it's very good. And it covers all the theory here. It's got all the equations and so on if you want to go into more detail. So one thing I'm going to say is I'm going to neglect the 2R. I'll do that later on as well, but that just makes some of the maths a little bit easier. It means we're not constantly just writing out 2R for no real reason. Effectively, this is the 2R just means a kind of arbitrary phase shift, so it's like an arbitrary complex constant, which you're going to get in there anyway when you do some calibration. I'll also drop the explicit discrete summations, turn those into continuous integrals, so it's much more like you've got now a function that you're measuring around the array, and you integrate then around the array rather than doing lots of discrete sums. So that's just a kind of mathematical generalization of what we have on this line above. Now, one of the last things I wanted to talk about in this section, I think it's one of the last things, I can't remember exactly what's next, but we've got the Born approximation. So the Born approximation is essentially a single scattering assumption. So if you've got discrete scatterers, then you assume that there's no kind of multiple interaction between them. When we have extended objects, so the type you can see here, so this might be a kind of velocity inclusion or something like that, then what are the consequences for when we apply the Born approximation? So you can see here we've got a source and receiver and our scatterer in the middle, our extended scatterer. And what we can do is we can treat this as lots of small elemental scatterers. And then under the Born approximation, we can just take a single scatterer with our incident field here from the source, and we can get our scattered field from that, which goes out to the receiver. And under the Born approximation, we can simply sum those up in order to get the total scattered field. Obviously, we are making a little bit of an approximation here, an assumption that the wave is not distorted as it passes through. So effectively, as it comes down to one of these points within the scatterer over here, you would expect to have some kind of phase shift as it travels through. I might actually have an illustration of that. No, I don't. Or have been distorted as it travels through. So this assumption of independence for all the points is never 100% valid, but it's a decent approximation provided that distortion is low, which means you need to have a small object of low contrast for the Born approximation to hold. So that basically covers some of the background theory that I'll build on with the rest of this talk. So in the second part of 3, I'm going to be talking about standard tomography algorithms. In particular, we'll look at ray tomography, diffraction tomography, and also how diffraction tomography links with the total focusing method. So I'll bring some bits in there. So ray theory. Again, we've got this setup which you're very familiar with. You have n sources, n receivers. I think in the vast majority of cases, n is equal to m. I suppose I had both just to kind of keep it a bit more general here. And we have what we call a full matrix capture. I've not introduced that so far, but essentially this means that you end up with n times n signals because you do all the different send and receive combinations. So you transmit on the first transducer, you receive on all, you then transmit on the second transducer, you receive on all, and so on, such that you basically get all the different send and receive combinations. And then you end up with effectively a big matrix of signals, if you like. And from each of these signals, you can pull out an arrival time. So you can analyze the signal, see when you get the kind of first arrival within that signal, and that will give you an arrival time. You can store that in a matrix which will have n by m size. You then want to somehow invert that, and from each of these signals, try and get some kind of model to fit that. And we use ray theory often to do this. And here I'm just going to show this with the guided wave tomography type example, where I've got a cross section through fairly artificial defects. This is a very sort of flat bottomed hole, if you like. And this is just for illustration purposes. In reality, we obviously deal with more complex things. So a cross section through, we send on one side, receive on the other side, and we can calculate our arrival time fairly easily just from the time it takes to travel in part A, which will be A divided by C within that region. So obviously, as we looked at before, velocity is a function of the thickness. So C is a function of T1 within this region. And then you go to this middle section here with a thickness of T2. C is now a function of C2, so it's B divided by C. That gives you your time in B. And then similarly, you've got a time in travelling through this part as well, so it'll be c divided by this. Add all those up and you get your total arrival time, the time it takes to transmit from here to here, and you can then start to compare some of these with your measured signals. So the principle of ray theory, essentially we use ray theory to predict the arrival times for a grid of thicknesses, or more general, a grid of velocities, if you like, here. And we can, using the model I just described, we can predict the arrival times, let's say. We can then try and invert this. We can either do this using a sort of straight ray assumption, which is actually perfectly an analogy of CT. So where CT reconstructs attenuation based on the amplitude drop of transmitted signals, you can do straight ray ultrasound velocity tomography using the arrival time shift as a result of the change in speed, or technically we tend to reconstruct something called slowness, which is the reciprocal of speed instead, but I won't go into that in any detail here. Instead, what we actually tend to do when we do our inversion is a gradient descent type method, which involves projecting residuals along each ray path. There are plenty of there's plenty in the literature on that, but you can also, through this process, because it's an iterative process, you update it each time, you can account for refraction as the rays bend, well, by bending the rays as you step through the routine. And here are some results. So we've got a thickness map that you can see here. This is our true thickness map. This is just simulated data to illustrate it, but it's fairly deep. So it goes down to 50% wall loss. I think this was the A0 mode at 50 kilohertz. That's our true map. This is ray tomography. And you can see that it's not a great reconstruction. You're getting something overall as a rough estimate, but it's not getting into fine details. So the point is that the ray tomography can get the overall behavior, but it can't get any fine details. And this is because ray theory ignores diffraction, which is a scattering which occurs at the small scales. So you're not really able to capture any of the sort of small scale variations. Because that all just gets diffracted out of the signal. So to try and address this and try and get better resolution, we can resort to something appropriately named called diffraction tomography. What you can see here is, again, we've got our sort of our patch that we're trying to image, and we've got our imaging point X. And we've got a source over here and a receiver over here. And again, source transmits wave in, gets measured by receiver. You've got source direction, receiver direction, and it's far field, so you've got plane wave assumption. So we've covered all those bits, and X is obviously our pixel location here. So we can calculate our incoming field in the frequency domain just using this plane wave assumption, plane wave approximation. We then have scattering potential rho from this one particular point. And we've then got the outgoing field from that point, pretty much as we had before. So if we want to calculate then the field that we would receive from that particular point scatterer under all the kind of assumptions that we've looked at so far, we can essentially multiply these all together. So we've got our incident field multiplied by rho multiplied by our field going out to the receiver, and this can be simplified down, effectively combining the exponential terms into one exponential that you can see here. So this would be the scattered field that we receive for a particular source direction, receiver direction, given by this expression with the dot product in there. So we've done this for one sort of element of our scatterer. We actually then want to sum this up for all the points in our scatterer. So we do this with this sum here. Again, we're going to drop the 2r like we did before, just keep things a bit simpler. And we'll also change from this discrete sum of all the points in the scatterer into a continuous integral. So we'll replace this sum of rho values with an integral of a more continuous object function. We'll call this object function O, as a function of x, which is the position in space. So you get this integral term across x. I won't give the derivation of this. Again, Kaken-Slaney gives a good explanation. The object function is given by this expression here, and essentially the point is, you might be able to work this out, but the velocity, essentially if you've got a large velocity contrast, then the object function becomes larger, and if the velocity contrast drops to 0, so c0 or c will be equal to c0, this will go to 1 squared minus 1 gives you 0, the object function will go to 0. So in the background region where you have no velocity variation, this object function will disappear to 0. So this is where our equation, based on all the assumptions we've got to, ends up. We end up with this this term here. And what we notice, we've got some function multiplied by an exponential term, or an oscillating exponential term, integrated, and this corresponds to a Fourier transform. Okay, so if we then express our object function, or the Fourier transform of our object function, with this O hat term, then our scattered field for a particular send-receive direction will be given by the term in the object function expressed as this vector term. So obviously this is actually a two-dimensional function, so we do a 2D Fourier transform, and then this is a two-dimensional vector term which tells us which point in the Fourier transform will correspond to this particular measurement. So we've done some interesting mathematical tricks in order to get to that point. Let's have a think about what that actually means in reality, try and illustrate this. So here you've got a particular source and receive direction with our circular array and our scatter in the middle. And we now introduce what's known as K-space. So this is something particularly is talked about in medical imaging, particularly for MRI. They talk about K-space a lot. We'll talk about it here. So essentially K-space is the Fourier transform space of, or Fourier transform version of reality. So rather than having, if you're familiar with Fourier transforms for frequency or for time to frequency domain, things like we talked about earlier, we're now transforming from, say, well, we'll just do 2 dimensions here. It could be 3 dimensions, but you do a Fourier transform along each of those dimensions, and that gives you the kind of spatial Fourier transform. And obviously the center point here corresponds to the low spatial frequency components, whereas the high are the rapidly varying ones. And we can look at this equation up here, and we can start to work out what different measurements, so this measurement here, would correspond to in K-space. So you've taken your actual object, you've done a 2D Fourier transform, and the measurement that you've got here will be this particular point here in K-space. Okay, so that's based on doing K multiplied by SS, which takes us in this direction, and then K multiplied by minus SR, which takes us back in this direction and gets us, when we kind of add KSS plus minus KSR, then it gets us this point here. Hopefully that makes sense. And so that's our one particular measurement. Then if we look at all the data we've got within our array, what we find out is actually our receiver will vary around this point. We have other measurements. And as we change the receive direction, we will get other measurements, as you can see, plotted around like this. Now, obviously, as we extend the receivers all the way around, we get 360 degree like this, so we actually end up with a circle in K-space. The radius of this circle will just be given by S. The radius will be given by K, because obviously SS and SR are unit vectors. They're just describing directions for the source and receiver. So that's where you'll get this particular circle from, which will obviously go through the origin. And then obviously you can change the source as well. We've changed the receiver so far, but if we start to think about changing the source, then our source vectors will change to these points in K-space, and therefore we will effectively map out a circle each time for each one of these sources as we go around the receivers. And obviously this will be sampled quite a bit closer than I've illustrated here, but if we do that, then we end up fully populating this circle here. So this is actually known as the Ewald limiting disk, or sphere in 3D. And this has a radius of 2K, and essentially through this we'll be able to get all information from about the 2D Fourier transform of the object under the various assumptions we've made, Born approximation, far field, etc. And interestingly, this 2K limit, if you think about what that means, it actually corresponds to a resolution limit of half a wavelength. So when you come to Fourier transform this back, you can get everything below a particular spatial frequency, but nothing above. And that's a resolution limit, and that relates to or essentially it's another kind of demonstration of the diffraction limit and half wavelength resolution that is very well known. So that's a kind of interesting illustration, and it does lead to a potential approach for imaging, basically. So the idea is that we can get all of our measured signals and assemble them into K space. So this would generally mean you need to resample, get each of your measurements, and then put them into a uniform grid, which wouldn't be easy because you've got those sort of circular patterns. Then you get that grid, so you need to obviously make sure that interpolation is done well. And then you can inverse Fourier transform back. So this is kind of illustrated here. So our diffraction tomography image at X is the kind of inverse Fourier transform in K space of the forward equation that we had before. Okay, so this is take our signal, inverse Fourier transform it. And we can compare that then to the TFM image. So this was frequency domain TFM with plane wave assumption. And what we can see is that these are really very much the same. So it's exactly the same equation within the integral. The only difference are these particular terms here. What are we integrating over? So in TFM, we integrate over the array, or we sum across the array, whereas in the diffraction tomography, we're actually summing across K space instead. And diffraction tomography is a bit more quantitative. You think about derivation we've done of the Fourier transforms and the theory and so on. So this is a slightly preferable one, whereas this will introduce some weightings into different components if we're trying to do quantitative imaging. So we'd rather have it in this form. Just to illustrate some of these wave number components, and the kind of consequences for this integration and why it matters. This is the kind of illustration of 32 elements in a circle. And you can see the kind of arc patterns that I illustrated before in here. And you can see maybe they're getting points very close together at the inside, also getting close together at the outside in that radial direction. Things become a little bit more obvious, or the spacing becomes a bit more obvious if you look at 256 elements. You can see here that, yeah, towards the edge you get a lot of sampling, towards the center you do. It's a bit sparser in the middle. This does actually, this whole similarity between the two equations does give another approach for doing diffraction tomography. So rather than interpolating, we can effectively do the TFM approach, so simply sum up for all the send and receive combinations. But we can also then introduce a weighting which accounts for the non-uniform sampling. The equation is shown here. If you're interested, I can give you a reference for it. In fact, there is a reference down here. There are other ways of calculating it as well, which look at the kind of Jacobian of the transformation between the two matrices, so that could be interesting to look at too. Essentially you can convert it to TFM image by incorporating this weighting term, and this will then lead to the diffraction tomography algorithm producing quantitative images. So map of that object function which relates to velocity. If you remember from earlier on in the talk, the velocity is the thing that we're usually trying to get hold of. formulation that we just looked at does actually give us some interesting insight about the wave number components and what these all actually mean, what they correspond to, how that relates to the physics. So what these different measurements tell us about the scatterer. So if we go back to our standard diagram again, we've got the equation at the top there, and we've got our send and receive direction. We've got our equal disk and K space here. I've just illustrated a kind of through transmission measurement here, and following our vector forms as before, we end up with this corresponding to a measurement about here. And what we notice is that what tends to happen, particularly as we get to proper through transmission, the two vectors end up lying on top of each other and cancelling out and ending up right at the centre. But basically, through transmission corresponds to all these parts towards the centre of K space. So we end up with the low spatial frequency components, the low resolution parts of our reconstruction. However, if we then look at more of a reflection part, so the kind of reflection subset over here, then we draw the vectors out. What we find is that the reflection parts correspond to the outer parts of our E-wall disk, our high spatial frequency components. But our reflection parts can't really tell us very much about the center of this, the low spatial frequency parts, and that can be important in quite a few cases. And this actually corresponds to a real life scenario that you might imagine. So here we've got a layer, and we've got background velocity C0 here and here, whereas in the middle you've got a particular layer C1. You've got an incident wave coming in here, and you get a reflection from that. Okay, and that reflection part tells us information about where the boundary is. Okay, you can use the time and so on to get that sort of information. Here you've got a transmitted part, and you get a phase shift as you travel through. And this transmission will encode information about the material properties. Now, whereas the reflection won't really tell you anything about that. It might give you an idea of the change if you look at the magnitude of the reflection coefficient, but it's less quantitative and it doesn't really encode as much information as this transmission measurement does with its phase shift. Another thing we can do is to investigate limited view cases with this K space. So if we now have our source above, receiver below, like we talked about before, we look at the vectors you can get from this. We get something like this, just for this sort of simple case. And if we actually plot all these out, varying across the receiver and varying across the source, we end up with this sort of, it's not really an infinity symbol, but the shapes you can see here, maybe somebody can let me know what shape this really is. But essentially you can populate these areas, and you'll notice we have large areas here, particularly close all the way down here, close to the center, close to the low spatial frequency components, where we're missing data, and that's potentially problematic. So next up in our outline, the third part is we're going to look at new tomography approaches. We'll look at the Harvard algorithm that I've done a lot of work on through the years. We'll look at Harvard-ISM algorithm, which introduces an improved scattering model. We'll look at SH1 tomography, so that's another improvement that we've looked at, as well as the Viscit algorithm, which is a way of dealing with the limited view problem that we've just talked about. So I'm going to briefly mention breast ultrasound tomography. So we've done quite a bit of work in medical imaging and medical ultrasound tomography, and this is an example of breast imaging. So here we've got bent ray tomography we looked at before, low resolution. This is the breast that you can see here, and we've got our array here. It's a water background, and this is the thing to be concerned about. This is a cancer mass. This is what we're trying to detect. This is obviously a very large example, whereas in reality they'd often be much smaller, and the ray theory wouldn't enable us to detect it. So that's the ray tomography reconstruction. And over here we have diffraction tomography. This is obviously higher resolution, but isn't really capturing any of the kind of general details that you got within ray tomography. but there are some true features in there, maybe the skin that you could see on this reconstruction. The point of Harbert, which is the hybrid algorithm for robust breast ultrasound tomography, is to combine these two together, so get the best of both, get the high resolution parts from diffraction tomography, but the low spatial frequency components from ray tomography. This essentially enables us to bypass the Born approximation, which is coming in to cause problems with diffraction tomography here. And you can see we get pretty good reconstruction here. There's more information in that paper. So the Harvard algorithm then, to just give you an idea of the concept, we've got our source here and receiver here. And in reality, what happens, as kind of discussed before, the wave distorts as it travels through. And the ray theory can essentially be used to correct for or account for the distortion that happens to the waves as they travel through. You use the initial guess from the ray tomography map, that velocity map, to say, okay, well, you should get this much distortion you can travel through, correct for it in the diffraction tomography reconstruction. And this is what happens if we then try and apply this to guided wave tomography. So again, this is an artificial simulated case. I think again A0 with a sort of artificial defect. Ray tomography, low resolution. We looked at that before. Diffraction tomography. Now this violates the Born approximation fairly clearly. In this case, it's too high contrast, even though it's relatively small. I mean, it's only a few wavelengths in size. This defect. So not great in this case. With Harbert, we can combine the two together, and you can see that actually we've got a significant improvement. So a lot of these features maybe kind of correspond to the original. You can see that there. Now so far we've basically taken ray tomography and applied diffraction tomography to improve it, and it's possible to essentially do the same approach again, improve Harbert again, iterate it, and if we do that, then we get this reconstruction here. So applied to diffraction tomography again with this as the background, and this is what we get. You can see it's improved a bit further. If we iterate this process over and over again, then almost like magic, then we can see this reconstruction here. We're getting very close to the original. And just to illustrate this point, we've got a cross section through the deepest point, and we're fairly close to getting that within 0.5 millimeter in this case. So that's the important metric for industry to know. So pretty good, pretty pleased with that result. So Harbert essentially is higher resolution than ray tomography, but it is more widely applicable than diffraction tomography, and this is just illustrated here. So more widely applicable because we get around the issues of the Born approximation. We don't need to just do small reconstructions. Now we can look at the resolution as well. So this is something that we did. We just made a sort of slightly artificial thickness map. We did standard Harbert, and from what you know before, we should be able to get half a wavelength resolution out of diffraction tomography type methods. And you can see if we actually take this true thickness map and filter it down such we get this half a wavelength resolution, you can see we get this reconstruction. It's not too distorted. We're probably losing this defect here a bit, or this component here a bit. So it's a bit blurred, but it's certainly much better than if we just have standard Harbert. And why is that? Well, we'll try to investigate this and try and find out what's gone on. And one of the main things is that we've assumed that the scattering potential from any kind of elemental scatterer, going back to this slide, is non-directional. So it's just a single constant regardless of the source and receiver directions. In fact, if we actually analyze it and look at what happens as the guided wave does scatter from a real defect, you can see that we make in black this omnidirectional scattering assumption, which is talked about, which is the kind of acoustic velocity scattering on an acoustic medium will behave in this manner, whereas a guided wave scattering from a thickness map, so the A0 mode in particular, will produce something which is kind of omnidirectional, which you can see illustrated here. we get these kind of very notable nodes. And where this becomes quite relevant, as we talked about here, so in through transmission, you get low spatial frequency components. Reflection, you get high spatial frequency components. In the through transmission regime, you can see you get, and there's always a bit of deviation, but there's not too much deviation between the blue and the black lines up until this particular angle. Obviously, it's slightly arbitrary where you draw the line, but I've drawn it here. And within this region, this red region here, we can say we get good matching. After that, it's not good matching, and it's not really good enough. And therefore, we're limited on how high spatial frequency components we can actually pull out. So we're only up to this particular point. And this corresponds to a resolution limit of around 2 wavelengths. So as mentioned, this is for the A0 mode, and I think it's 50 kilohertz for about a 10 mil thick plate. So that's our finding, and this was something that wasn't understood at all really before. So that's where our resolution limit is coming in, and that explains this this issue that you can see here. So the question then is to how to improve this. Kind of 2 parts to this. So one approach is to capture the physics better. So we could replace our constant rho that I just described with a rho which is a function of both theta and the local wall loss. How do we do that? Well, we can approximate that from an FE method. So effectively, so we can then, assuming we then know that, we can then perform an inversion using this new information. So effectively it's Harbert with the improved scattering model, which we've called Harbertism. If we do apply Harbertism, then you can see we get a much better reconstruction here. As I mentioned, we approximate this from the finite element method. We effectively expand this into orders of like sine functions of might be cos functions actually of theta, and then thickness as well. It's polynomial with thickness. And I think with just 12 coefficients, you can actually characterize this function quite nicely, and that's what I illustrated on the previous slides. So this is a form of regression, or if you want to go into the machine learning side of things. And there's more in this paper here. So that's one approach, and it can be a little bit fiddly to implement. So another idea is to try and use a different operating point. So here again, we've got the dispersion curves that we had a bit of a look at earlier. I've now marked on the higher order modes, and I should say thanks to Mike Lowe, my colleague, for helping produce these dispersion curves. The point is we've been operating down here so far, so A0 at 50 kilohertz for 10 mil thick plate. In the past, we also had a bit of a look at S0 in this particular region here. So obviously higher frequency. So high frequency tends to mean a shorter wavelength. Everything else being equal, however, here things aren't equal, and obviously got much higher velocity. So in reality, our wavelength for 10 mil thick plate at those 2 particular operating points tends to be about the same. So I think it's around 40 millimeters for these 2 regions. So actually S0 doesn't give you very much improvement in the resolution in that region. So possibly you could go on to higher order mode, just to say there's not much point in doing A0 or S0 up here because the dispersion is too low. We won't get very useful information. And also up here, there are other problems with other modes coming in. So A1, in theory, you could try and aim for this particular point here, but extracting that mode is going to be very difficult. You're going to have a lot of stuff going on, trying to pull out that one mode at that one point without getting too many other parts in. It's going to be very, very difficult. So what we can do instead is we can look at using SH modes, because there are more than just the LAM modes that we have in the pipe. So SH, shear horizontal modes, these are modes going in the, say, propagating in this direction. Say your plate is sort of something like that. Propagating in this direction, you get shearing motion like this. So this would be SH0, whereas SH1 I think is the first order one where it kind of shears top to bottom like that. SH2 is another kind of even higher order version of that. And because you've got this different shearing direction, you don't tend to get coupling between SH1 and S0 or A0, for example, or certainly when you come to excite, you can excite pure shear horizontal much easier than trying to excite pure like S8, S1 or A1 or something like that, because they've got very distinct motions. So that means that if we select a region down here of SH1, you can excite in a pure way, or at least in a way you can separate it from SH0 without exciting S0 or anything else. You have sufficient dispersion in that region, and so on. So it's quite a good solution. I should say thanks to my PhD student who finished a few years ago now, Andy Zimmerman, for producing this map. Apologies, it's different color scale and things, but that's just where we are with it. And we produced this reconstruction here. Obviously, it's a little bit noisy, but you can see this is much higher resolution than the standard A0. You can see these boundaries, for example, are very, very sharp, which is much more of a reflection of the original thickness map compared to the A0 case, where it's really very blurred. You're not getting very much in the way of detail in that. So the last thing that I wanted to cover was the limited view tomography, because I gave some examples of this, or gave an application of this earlier on. And so I'll cover some of the theory first of all as to what we can do about this. So this is our original model. We've got the Fourier components that look something like this. I explained where this comes from before. So you get everything within these two regions. And if we say that everything that's unknown in this dark blue region in the background is just unknown, so we'll set that to 0, just leave it on 0, then we get a reconstruction that looks like this. So some very common limited view artifacts here. If you've done radiographic CT, I'm sure you've been taught about these sort of cross patterns and so on. But yeah, you can see these cross patterns. You'll also notice that the contrast is reduced within this sort of center region. And the question is, rather than just using zeros for these unknown terms, can we find better values to kind of populate those regions with? So expressing this another way, we've got our measured data from above and below, and we can put this into our limited view reconstruction, and we see these sort of artifacts that we had before. And in this case, we're trying to effectively find values for two arrays either side of the scatterer to kind of complete this array and turn it into a full view array. And how do we do that? Well, what we can do is we can try and look at this image here and split it into two regimes based on the contrast of each pixel. And we say that below a particular value, so well, above a particular value, these values seem to be true. They seem to correspond to the true features. So anything above, say, 0.55 tends to be in this kind of orangey, reddy region, corresponding to the true value. And then at lower contrast, all these bits out here, lower contrast values seem to be artifacts. They don't tend to be real things at all. So the idea is that we can maybe split this image into two parts, maybe apply a threshold or something to reduce the artifacts part, and then use that information to populate what's missing in our limited view reconstruction. So with that in mind, we take our limited view reconstruction, we apply a threshold to remove the kind of background artifacts. Then we generate a full view data set. So it's necessary to do it this way around, but generate a full view data set, combine that with the original data you had, and then reconstruct that, and you have an improved reconstruction. So effectively, we combine this thresholded image with the actual measured data that we had in our original limited view reconstruction. You can see this is much better. So the contrast is better, the artifacts are reduced, and so on. And also, we don't just stop there. We can go on and iterate the process over and over again. So one point I wanted to mention here was that these processes are linear. So obviously under the Born approximation, which we'll be assuming just for illustrating it, although there are ways around that. this process will be linear to generate this full view data set, and then the inverse will also be linear. That's just that kind of Fourier transform idea back. Now, because both these are linear, we can take a bit of a shortcut. So what I'll do now is I will just generate a limited view data set from my thresholded image, and then I will generate an image directly from that. So put it into the image space here. And what we can see here is that I've basically generated the same image that I got before, but by doing this sort of mathematical trick of image B minus image C added onto image A. So if you want to think about that another way, we've got our image A, which is missing various components. We set those to 0, if you remember. So we set the missing components to 0. So we then want to add on some components that are going to populate those missing parts. So what we do is we do image B, which is an improved thresholded image, minus its own limited view version. So you don't want to overlap the limited view components again, so you just want to take off, so you effectively subtract off the limited view version of B from itself. So you subtract image C off from image B to just get the missing unmeasurable components, add that onto A, and you can see this improved reconstruction that we have here. And highlighting the importance of this B minus C component. So this is the virtual image space components that we are gathering, and this leads to the name virtual image space component iterative technique, or VISCIT. Iterative obviously being that you can iterate this process over and over again, which is what we've talked about before. And as I mentioned, this is in the literature, that reference there. Just to give a sort of more concrete, realistic example, here's a simulation with, I think this is very low contrast, but it's obviously a more complex defect, and you can have the threshold, and you can kind of move the threshold down each time as you go through the iterations. Here we have standard Harbert, and as you can see, you've got a lot of these diagonal artifacts and so on. It's low contrast and not a great reconstruction. If we apply VISCIT with this thresholding method, you can see we get a much better reconstruction that you can see here. And this has been demonstrated experimentally. So we've got here kind of ultrasound mirror agar specimen. And the point of the agar specimen is that we can, without having to put boundaries in, because the boundaries can be sharp and going to introduce some reflections, what we can do is we can use an agar block and then make holes in it, and within each hole we can fill a different kind of water and ethanol mixture in order to control the wave speed within that region. So first of all, we look at a reflection image, and what you'll notice, well, there's not much to see, so we can't see any reflections from the boundaries. So just to say, this is from a medical ultrasound scanner, so this is it's effectively using total focusing method to generate its reconstruction. However, if we then put into each of these, or well, effectively got into each of these the different ethanol water ratios, and we look at the transmitted components, look at what gets reflected off the back wall back to our measuring array, you can see that we get this reconstruction like this. It's 1.3%, 3.1, 4.5% values of, I think that was, let me just check, I think those were the mixture percentages, that might be contrast. But anyway, it gives you an idea. Here we go. Oh no, so these were, ethanol fractions were 5%, 10%, 15%, and that will correspond to contrast, velocity contrast, so of 1.3, 3.1, 4.5%. And you can see this nicely here. We've got our measured sound speed, which we just did through independent measurements of those particular liquids. And you get the sound speed from the VISCIT image, and you get pretty good correlation. You get fairly accurate reconstructions of that. So overall, quite a nice result there. Oh, so it's been quite a long talk. I'm feeling pretty tired by the end of this. I imagine you could probably look at it in a couple of stages if you wish. But got some conclusions here. So essentially, I've talks a lot about various different parts of tomography. I've demonstrated the Harvard algorithm, hopefully explained the Harvard algorithm to you for guided wave tomography, so capturing ultrasound wave physics for improved results. Harvardism then improves the accuracy of the reconstruction. So that's for guided wave tomography, where we've got this different scattering behavior and we can capture that in what we're doing. SH1 tomography can then improve the resolution to the necessary level. So this is kind of oil industry. They want to be able to detect a defect at I think 3 times wall thickness. So 3T is the kind of example thickness. So we need to get at least that in terms of resolution. And switching to the SH1 mode, which has shorter wavelengths, was one very clear way of doing that. And finally, we've introduced the Viscit method for doing limited view imaging as well. And that concludes my talk. So I hope you found it useful. Obviously, happy to answer questions. Obviously, I've also glossed over an awful lot of stuff. However, I have given references to various things, which I hope would be useful for anyone as well. Yeah, that's it. Thanks a lot.